Right, this is the answer key video for the topic 5.9 practice problems on steady state approximation. Okay, so basically here, this ties really nicely with 5.8 on reaction mechanisms and the connection to the rate law. All right, the difference between 5.8 and 5.9 is where the slow step is. Okay, so in 5.8, or even in earlier, we did 5.4, okay, we had the slow step, the slow step being the first step of the reaction mechanism, okay? And again, the slow step is rate determining. All right, so for this one, it's real simple, okay? It's just based on the rate of that first step. Now, in this one here, 5.9, steady state approximation is talking about when we don't have the slow step as the first step, okay? Because if we look here in this example, you have B, okay? And B is created or produced, and then it is used. All right, so B is what we call an intermediate. Okay, and intermediates right here should not appear in the overall reaction. Therefore, it cannot appear in the reaction rate law. Okay, so that's kind of one of those minor things there. All right, so because of this, right, we can't have an intermediate in the reaction mechanism. We have to then do this topic here of steady state approximation, okay? So what we can notice here is that we have a double-sided arrow, all right? And that means the reaction can go in what's called the forward reaction. So this here would be the forward, all right? And if it's going in the opposite direction, that is called the reverse, okay? So forward, reverse. All right, and they both have a K constant associated with them. But again, these are going to essentially be the same because the rate constant should not change for the reaction. So again, if this is freaking you out that it's K to the -1, ignore it. They're both K's here. They're the same exact thing. All right. Now, what we can do here is we have to first make sure that the mechanism is valid, meaning when we cancel these all out, these individual steps add up to what we need them to be for our full overall reaction, okay? So this here is our overall reaction, okay? And this here is our observed rate, okay? This is what we get experimentally, all right? And since the second step is rate limiting, that's what we're going to use. Again, this is, as we said, our slow step or our rate determining. Okay, now with this rate determining step here, okay, we then can go and we have to conclude all the steps above it because of the use of this intermediate here. So what we do is we ignore that and we first look at that reaction there, okay, where the rate of the forward, okay, the rate of the forward, that's talking about the A plus A goes to B, is equal to the rate of the reverse when B goes to A plus A or 2A. All right, so if we were to write rate laws for both of these, okay, the first one would be that the rate is equal to K times A squared because there's two of them. And the reverse is going in the opposite direction, still the K constant, right? But B is now the only reactant, and it is to the first power because there's a 1 coefficient out in front, okay? Then from there, in order to get to our next step, we have to isolate our B, all right, or isolate our intermediate, okay? And by that, we do mathematics, and we divide both sides by K to the -1, okay? And if this step confuses you here, you are welcome to cross these out because those are going to essentially be the same thing, all right? But you will see it written that way, but if it is confusing to you, you're welcome to ignore it because, as you can see here, we're going to combine all the K values into a single K constant, okay? So we're going to combine all of those together into this new thing called K, all right? So again, all of these individual Ks, right, are for either the forward or the reverse or step 2 or step 1, but at the end of the day, they're all going to combine and give us one overall rate constant for the reaction, okay? So if we then solve, we now have our intermediate, B here, okay? So then what we can do is we can take B, so that's everything over here, and we're going to plug it right in to our rate based on our slow step, because again, you can't have an intermediate in the overall rate order. All right, so we replace that right there, and we get, all of our k's, a squared, and c. And then again, as we said in the last step, we're going to combine all those k's to give us one finalized rate constant. Okay, so that is, again, how you do the steady state approximation for when the slow step is not the first step in the reaction. And typically, if you see anything like this, the slow step would be the second step. Okay, so you only have to deal with step 1 and step 2. All right. So, pretty much right there, that's the I do problem, okay? So, if this is our reaction, our overall reaction, okay, the experimentally determined rate law is the following, okay? We have this right here. So, the reaction occurs in two steps. So, what is the rate limiting step? Okay, and the rate limiting step here, since this is our rate, okay, and it doesn't perfectly match either one of these, okay, that means we had to have made a steady state approximation. Okay, so what that means is if it was one of these individual steps, right, if it was this first step here, okay, and this was our slow step, again, slow means rate determining, we would just use the coefficient out in front, that 1, and that would be our rate. But since that does not match up there, that means that our second step has to be the slow step. And that, again, in order to get this rate, we're going to have to do a steady state approximation. Okay. So, we all agree now that the rate law is based on step 2, okay? And with step 2 here, though, the rate is equal to K2, right? And the coefficients of both of the reactants. However, what we have to notice here is that O is an intermediate. So, we have to solve for O and then replace. Okay, so again, right here, this is the rate of the forward equals the rate of the reverse. All right, then to get this here, we got to solve for solve for O by dividing both sides by K. All right, once we've divided both sides by K here, we can then get O by itself. Then from there, we plug this back into the rate given right there. Okay, or more appropriately, we're going to plug it in right there. Okay, so we're going to plug all of that into where we see our intermediate of O. All right, from there, it's basically combined. Okay, and then what you can see here is we have two O3s. So since it's multiplication, that's going to become A squared. All right, and all these K combine to give us just our one rate constant for the overall reaction. All right, so that's steady state approximation. Again, we do problem. Make sure you're watching the video. Explanations within that one. All right. First problem here. A reaction is proposed to take place in the following elementary steps. Okay. If the rate law of the reaction was found experimentally to be the following, which step must be the slow step of the reaction? Okay. So if we look at step number 1, if this was the slow step, okay, this would be our rate, but to the power of 1 and to the power of 1. But since we have squares here, that means that one of the following has to be a slow step. Okay, so we're either looking at step 2 or step 3. And this is a very long-winded explanation, okay? But basically here, when we do this, if step 2 was the slow step, we would solve for the intermediate, and the intermediate would be D, right? And then we would... And that's what that's saying right there. We'd solve for D, okay, and then we would plug back in and we would get a rate that looks like this, okay? And obviously that rate does not match what we're looking for here, okay? If we look at the third one, okay, our intermediate now becomes E, so we have to solve for E, all right? And when we solve for E here, we also have to use step 2. And when we have to use step 2, we then also have to get rid of D from above, okay? So we have to use the work we did here. And long-winded explanation, when you plug all that in, we cancel out both of the intermediates from the above steps, and we get the finalized rate that we need, okay? Also, another shortcut for you here, just to give you a cheat code, okay? Obviously, this wouldn't work, all right, if you need to show your work. But in a multiple choice test here, what you should notice is is something along the lines of you have to be thinking steady state approximation, okay? And reason being, again, is because if it was the first step of the reaction, then our rate would be perfectly matched to those coefficients. But since this is a 2 and this is a 2, okay? What we can notice here is that if we just combined those two steps, we don't see another AB. We do not see something that would make this AB squared. All right. Even if this combines and that's C squared, as we see there, right, we still don't have another AB. So you could, on a multiple choice test, make a pretty good estimated guess based on the fact that you need 2 ABs and 2 Cs. Okay, so you could probably guess that step 3 is going to be our rate determining step based on this logic of steady state approximation. Okay. Step 2, giving the following 2-step reaction mechanism, identify any intermediate. So again, an intermediate is something that is made in one step and used in the other. Okay. Then for the overall reaction, we cancel out our intermediates and we combine any like terms. So again, for example, NO2, NO2, that's how we combine and get 2 of them. All right, CiNO2 or ClNO2, right? 2 right there. Okay. So then it says if the first step is the slow step, what's the predicted rate law? That just uses the coefficients out in front. Okay, pretty straightforward. 1 and 1. Okay, put it with a K for our rate constant. If it is the second step is rate determining or the slow step, then we have to use our steady state approximation, okay? So for this one here, we would NO2 and Cl, but since Cl is an intermediate, we have to try to get rid of this, okay? And that's what we're going to try to solve for here. All right, so in order for us to solve for Cl, we have to go back up to step 1, where, again, the rate of the forward is equal to the rate of the reverse. All right, so this pointing to the right is your forward, and to the left is your reverse. So if I write the first one here, okay, my forward reaction is K, NO2, Cl2, 1 and 1. In the reverse, we have a new K, right? And generally you're going to see it as a -1, right? In order to indicate that you're going in the opposite direction. And both of these to the coefficients of 1. All right. Then from there, we do some algebra and we divide by our K and our ClNO2 to move those to the other side to isolate our Cl variable. Then from there, we are plugging this entire thing back into there. Okay, so that's what we're doing. We plug that back in, right? And we get all these. All of your K's combined to give us 1K. And then if we have any things that are similar, like this NO2 and this NO2, they're going to combine. And since it's multiplication, you now raise that to the power of 2. Okay? So again, a very algebra-heavy unit here, or lesson. Finally, step 3, we have a fast first step and a slow second step, which means, again, the slow step is rate determining. And since that is our second, okay, that is our second step that is rate determining, we need to use our steady state approximation, okay? First one, write a rate law that is consistent with this mechanism. So, again, we're looking here, step 2. So, our rate is equal to K times our concentration of the reactants raised to their coefficients, which is obviously the first power. However, again, that's an intermediate. So we have to use our first equation, or our step 1, where the rate of the forward is equal to the rate of the reverse. Then we solve to isolate our C variable. All right, and then from there, we take this entire thing and we're going to plug that in for C. And since all of the K's cancel out, it doesn't matter, and it just gives us the final K and A over B based on the substitution. All right. Then the last one, what's the overall reaction? Well, with that one, you just combine everything and get rid of any intermediates or catalysts, and we get A goes to B plus D plus E. All right. So there's that one. Again, if you have any questions, let me know. I'm always here to help. Otherwise, have a great day.